Now let's look at some strategy on the cache performance improvement, especially by decreasing the miss rate. Okay, so we want to increase the hit rate somehow, because like penalty is basically depending on level of caches and what memory technology you're using and so on and so forth. That's more hard. It's harder to actually control than with some simple strategy we can probably improve the hit rate of the cache. Now what we need to understand, uh, first of all, one is we want to introduce more flexible placement of the block. As we have seen on earlier lectures, that a block address has a fixed cache line, right? And if that cache line is already filled up, we have a conflict, then we need to have a penalty for the miss. Uh, so, but with that example, what we have also seen that even if it has that specific index, that specific cache line is filled already, it might be the case some other lines are open, right, are empty, is not filled up with a block. So instead of having make that situation as a miss, if we can place the block in an available cache index, then it will basically help us to increase the hit rate. So here the approach we are thinking of, that we don't go to one fixed cache line to replace a block, but we see if there are other cache line which is available, which is empty, and we place it there. So second approach, as I was explaining in the previously also, it reduce the penalty. Okay, so you introduce a multi-level of cache. That means you are actually making more resources on the hardware side, like you introduce L1 cache, then L2 cache, then L3 cache, more faster and larger memories in the hierarchy. And also, of course, your RAM technology, make a faster RAM there, and that will boost up the performance. So so we want to make big cache and multi-level cache to reduce the penalty. Now let's look at more of this first approach, flexible block placement. So it is basically increase the search space. Okay, so far we studied about what we call a direct map. One block address or reference address is mapped to only one specific cache line. Now the approach we can do is a set associative. Maybe it is not only one cache line, maybe two cache line. Okay, that is a set associative, and we said okay, it is two-way associative or four-way associative. Two-way associative means a reference address can have two alternate placement in the cache line, like either cache line 1 or 2 or 3 or 4, something like that. And four-way associative is a reference address can have possible 4 cache line replacement. Okay, it can go 4 of them in the total number of cache line present. And full associative is the extreme end of the spectrum, other end of the spectrum, where a block can be placed in anywhere. Okay, if there is a place, the empty place, we just place the block. Okay. Now we talk about the strategy, but how are we going to actually manipulate it or operate it in the hardware? Like in the software term, it's easy. You can all think of like a table and search. If there is empty space, you go there, insert it and stuff like that. But however, in the hardware, can we do anything about these strategies? Yes, we can do that. We just reorganize the direct cache map into sets. So first, we talk about this one-way set associative, which is a direct mapping, which so far we have learned is that we have the cache line and a block can be placed at only one of them, right? A block address is still divided by your cache line mod you take, or remainder you take is your cache line index. Now imagine instead of having 8 cache line, you have 4 cache line, and you are just placing this line 4, 5, 6, 7 in place of 0, 1, 2, 3. So in this reorganization map, that means a cache line computation from a block address will be bound to this value 0, 1, 2, 3. But we can actually now test it has 2 alternate places to go. And if there is empty space, one of them is empty, we place it there without calling it as a miss. Similarly, 4-way set associative, in this example, instead of having 8 cache line, we maintain 2 cache line, and each line has 4 alternate places to place that block. 8-way set associative or fully associative would be something like only 1 cache line, and it can go all these 8 alternate places, hardware wise. So, 1-way set associative direct map, for example, that we had in the previous lecture, is something like that, right? Now, from there, if we want to do 4-way associative cache, then we'll pick up, like there was 1024 cache line, now we make them 256 cache line, but it has alternate 4 places. Okay, and then when you are accessing a cache, like trying to see if the cache is present in the block or not, we basically do this equality circuit for each section of this cache memory. And that means if the block is present in the cache, one of these equality and this AND check would be hit, right? So we are 4 of this hit and miss signal to make an hit or miss signal out to the controller or the memory module. And then what about the data? Data would be you're coming back data from the 4 sources here now, and it will be a 32-bit 4x1 multiplexer, and you pick up one of them. Whatever is matched, that line will be selecting your multiplexer. Now this multiplexer is a specific special multiplexer which called a one hot multiplexer. Means it has 4 selection line in this case, and such a way only one of the line can be one at a time. That means inside this block there is no need of a decoder. Okay, we have 4 selection line telling which one to select, and we basically select that data out of the multiplexer with using this one hot multiplexer technique. Now point is that if a cache line need to be replaced, which one would be, right? Now let's say there is a conflict and we see all of them are already filled up with a block. It's still a miss, right? Now this challenge comes as which line to be replaced. This first line, the second one, third one, or fourth one, right? We have couple of algorithm. We can make it on the hardware. One is least recently used, or LRU. That means a cache is not accessed for a long time, a cache line for a long time by temporal locality property. We can say, okay, its probability of being accessed is low, go and replace it. And random is another, go and randomly place, especially like if it is more than 4 way set associative, usually we go with the random, because like to track which one is the least recently used, we need to have more bits in your control line, in the control bit, and also that means you need to have a complex circuit to detect and determine which one is the oldest one among them. So with a 4-way set associative, still LRU we can do, but if it is more than 4, usually we just purge out one of the line randomly. We toss a coin and do that. Okay. Of course, it's not toss a coin inside the computer. There is a random generation circuit and you just pick up one value out of that. So that's all for this lecture 22, and that's conclude our study on the cache memories and its usage and its technique behind it. If you have any questions, send me email or update on the discussion in the Canvas or ask me in the class.